Hey, here we are. It's a Tuesday night, and it's another ham radio class. This is a general class for those who are looking to upgrade from the technician level to the intermediate or general class level. And I'm your instructor, Gary. Whiskey 4 Echo Echo Yankee is my ham radio call sign. And we work out of this book. It's the American Radio Relay League License Manual for the general class, the 10th edition. This is the most recent book, and it has all the questions and answers necessary for you to pass a 35-question multiple choice test. That's how you get your upgrade from technician to general, and we go chapter by chapter in the book, and tonight we're on chapter 7. Well, come on, take the laptop. Here's the schedule for the rest of the class. So tonight, chapter 7 on antennas, which is kind of interesting and fun. Next week, Dave will be back and talk to us about propagation, which is the other element, the things that gets our radio signal out to other hams. And then on the 31st, we will have chapter 9, electrical and RF safety. And then we'll take an intermission, and then we'll come back and take a 35-question multiple choice test together as a group. See how we have done so far. And then optionally, if you'd like to come back on April the 7th, we'll take 2 more practice tests together. So as a group, we'll in total take 3 practice tests. So come back to me just for a second, if you would. We talk about electronics, we talk about semiconductor devices and components and things like that, but you're probably not going to get involved in building your own transmitter or your own receiver. Maybe a kit. That'd be a fun thing to do. But all hams will likely build their own antennas. And put up antennas for different bands, try different things. This is where experimentation really comes to the fore. So this is not only a necessary chapter for the test, so that we look at the questions, but it's also a very useful chapter and a practical chapter. And I'd like to start with my own section, 7.0, which is a kind of a review of some past things that I've talked about in the technician class, but many of you may not have taken my technician class, which is available here on YouTube or via Zoom. So come back to the laptop if you would. So this is section 7.0, which is kind of a review. Okay, I call it Antenna Basics, Gary's Review. Come on, there we go, a building slide. All right, first thing I want to talk about, remember skin effect? At DC, when you're passing current through a wire, if you take a cross section of the wire, which is what we're looking at there on the top. Okay, let me get my laser pointer going here. If my computer will cooperate, there we go. So here, with DC or very low frequency AC, 60 cycles, electrons pass through the entire cross section of the wire. All of the copper, let's say, is being utilized to carry electrons or electrical current. But as the frequency goes up, as we move into the radio frequency range, something interesting happens. Because of the fields that are built up there, current only flows in the outer part of the wire. Again, this is the cross section of the wire. And in the center of the wire, no current flows. And the higher we go up in frequency, more and more this happens, so that in the end, at HF and certainly VHF, UHF, the RF currents that are being carried by the conductors that we are using is actually on the outer surface of the wire, and the inner section is not being used at all. And a trick question I have for my technicians is this one. At radio frequencies, how many conductors are there in this coaxial cable? Anybody want to hazard a guess? You can go ahead and unmute. Okay, I'll tell you.
3.
There are 3, exactly. You'd look at it and go, well, there's 2. There's a center conductor, and then there's the outer, braid, the shield. But actually, there's 3. And the third, so the outer surface of the inner conductor, that's 1, yep. The inner surface of the braid or shield is number 2, and the outer surface of the braid is a third conductor, which we sometimes forget about, and especially if we put dipole antennas up in the air and we connect it directly to coaxial cable, we forget that we're actually adding a third wire to that antenna that we don't even think about. So just keep that in mind. Another concept is that of the isotropic radiator, which is a point source antenna. It's a theoretical concept. We can't build such an antenna because of reflections and because of physical dimensions and whatnot. But engineers use it in calculation as a standard which they can measure. So if we had a point source antenna that had uniform radiation in a sphere all the way around it, that would be an isotropic radiator. And we can compare other antennas' gain to this isotropic radiator. Now, the more common antenna, and one that we can build, is the dipole antenna. It's a half wavelength long at its design frequency, which means that you have a quarter of a wavelength on one side. This is a center-fed dipole, and a quarter of a wavelength on the other side, and you're feeding the antenna at the center. And so with a coaxial cable, the inner would go on one of these, and the shield would go on the other. But remember, you've got that third wire going down here, which can sometimes cause problems with, why isn't my antenna tuning correctly? It might be that third wire, which is why we will put sometimes a choke here, which can be a ferrite, or you can take coaxial cable and wrap it into a coil of 6 or 7 closely wrapped coils of coax and cable tie it together. That can sometimes choke off current on the outside of the shield, or a 1-to-1 balun, also useful at a center-fed dipole. And how long is a dipole? We were talking about this before we got started. It'd be much easier if we could just stay in the metric system, but this is America. So we don't all do the metric system. So if you want to know the length of a half-wave dipole, this is nominally the frequency, the formula that you want to use. 468 divided by the frequency in megahertz, which will give you the length in feet. So just keep that in mind, because that can be helpful for certain test questions. In the email I sent, and I was very happy to hear that some folks got a chance to watch this video from the Ham Radio Now series. Gary Pierce put this together, and it's Standing Up for Standing Waves. Great presentation. And 2 things that I pulled out of it that I want to make sure that you're aware of. A quarter wavelength of wire, or transmission line, is an impedance inverter. What do I mean by that? So if this is the transmission line, and it's a very low impedance over here at a certain frequency, at that same frequency over here, it'll be a high impedance. It's an inversion, high, low, high, low. Whereas a half wavelength length of wire or transmission line is an impedance repeater. So if you have a certain impedance over here, and this is exactly a half wavelength long at that frequency, you'll have the exact same impedance over here. Which is why sometimes if you're putting a dipole antenna and you want to know what the impedance is at a particular frequency, you make up a special half wavelength of line, let that be pulled up into the air with your antenna, and then make your measurements on the ground, and you'll know that you're getting readings that are actually reflecting what's going on up in the air. And when I talk about impedance, we're talking about ratio, the ratio of voltage to current. So here we have the volts trying to push the amps through a wire, and you got Mr. Ohm resisting it there. So it's the ratio of voltage to current. And with a dipole antenna, we're feeding it here at the center again. I'll show you here that the current maximum for this antenna is going to be at the center. The current minimum is going to be at either end, and the voltage minimum is going to be at the center, and the voltage maximum is going to be at the end. It's this graph right here. So feeding a center-fed half-wave dipole antenna, maximum RF current will be at the center. And because of that, we say that the low impedance point, the ratio of voltage to current, says that this is a low impedance point, whereas here we have a high voltage, low current. This is a high impedance point. And I love this dynamic graphic. The blue is the current, and you can see the amplitude is highest there at the center, smallest at the ends, whereas the voltage in red is highest at the ends and lowest at the center. And Ohm's law for AC circuits says that you can use this to do some rough calculations. Now note that when reactances are involved, it can throw this off, but this assumes kind of a resonant circuit. And in a resonant circuit, remember, the inductive reactance and the capacitive reactance are equal in value, and they cancel each other out. So a resonant circuit, the capacitive reactance and the inductive reactance cancel each other out, and you're left with just resistance. And with antennas, there's two kinds of resistance. Good R, which is radiation resistance, which is what is used to radiate signals out into space, and poor connections, corrosion, things like that, that's called bad R. That just results in heating. So again, to review, the center-fed dipole, the lowest impedance point is at the center. We say the impedance of a half-wave dipole is nominally 73 ohms. I'm going to show you where we get that from in a second. And at 73 ohms, if we had 1 amp of current, well, that would put 73 volts at the center of that antenna. And with 1 amp of current and 73 volts, that would be 73 watts of power. Just some things to be thinking about to give you perspective. An end-fed resonant antenna, a lot of times you'll see these in the ads and whatnot, is a voltage-fed antenna. It's a half-wave dipole antenna that is fed at the end. So at the end of the antenna, the impedance is going to be very high. So if you're feeding with 50 ohm coaxial cable, you're going to have to transform that up to a very high impedance with a 9-to-1 balun or greater, 64-to-1 balance I've seen. The voltage will be highest at the feed point. The current will be the lowest there at the end, but power will be distributed across the antenna in the same way. But remember that third wire, the coaxial feed line will likely radiate on the outside unless you add something called a counterpoise. That's why you're feeding here with coaxial cable. There'll be a terminal here that says go to the antenna, and there'll be another terminal that says for the counterpoise, which should be a quarter wavelength at the frequency that you want to use, a wire hanging down from the end fed. If you don't do that, then you will have RF current on the outside of your coaxial cable, which may distort the pattern and not give you the kind of results you want. So we mentioned the lowest impedance for a dipole antenna is at the center, but if you move the feed point not to the end, but just to an intermediate point, you can actually feed the antenna here with a 4-to-1 or 6-to-1 balun, nominally about 200 ohms, and this makes what we call an off-center fed dipole, sometimes wrongly called a Windom antenna, but off-center fed dipole. One neat thing about an off-center fed dipole, the basic half-wave dipole is a single band antenna. With the exception of if you put a 40-meter dipole antenna, it will work on the third harmonic, which is 21 megahertz, 15 meters. That's the only exception to the rule. It works third harmonics, okay. But with an off-center fed dipole, feeding here at this point, this antenna, let's say it's an 80-meter dipole, it'll work on 80 meters, it'll work on 40 meters, it'll work on 20 meters, and it'll work on 10 meters. Huh? How does that happen? Well, it's because the ratio of voltage to current at that particular point can be the same for all of those different bands. And so if we look at a VSWR plot of an off-center fed dipole, this is a 40-meter off-center fed dipole. So here's for 40 meters, but here's another resonance up at 20 meters. Here's another resonance at 15 meters. Here's another resonance up at 10 meters. So off-center fed dipoles are multi-band antennas. So for a half-wave dipole antenna, and also the off-center fed, the radiation pattern, this is the antenna here in the middle, going up like that. It's a donut going around the antenna. Now with reflections from the ground and whatnot, if we're looking down on the antenna, it looks like this. And if we're looking down on the antenna, moving the orientation, this is the antenna here, for example. So you see the maximum gain is broadside to the antenna. If we switch the antenna 90 degrees here, this is just a dynamic pattern of the transmit and receive, works in both directions. So you see there's very little off the ends of a half-wave dipole antenna. Now, with an antenna that comes down low to the ground, however, and it's hard for us to get our antennas up a half wavelength, especially at 80 meters, that'd be 120 feet up in the air. That's kind of hard unless you really got some tall trees or whatnot. So our antennas are typically lower than a half of a wavelength. And when that happens, we tend to get a pattern that is more omnidirectional. But if we can get them up high enough, here's half wavelength high, you can see there is directionality and higher gain in the main lobe. Now, for most of us, it's difficult to get the antennas up high. In fact, sometimes we can only get one point up high, maybe with a tree or a mast or something like that. So you can put up a dipole antenna as an inverted V. It's an upside down V, and support it at the center. Feed it as you might normally with a center-fed dipole, or you can do this with off-center-fed antennas as well. And this kind of an antenna was going to have mostly an omnidirectional pattern, something that looks like this. Remember, we're not tackling any test questions yet. This is just kind of review material. The most important thing I want to point out to you tonight for this review is this. So what we're looking at is antenna impedance here on the vertical scale. And we're looking at height above ground in wavelength on the horizontal scale. So here's a half wavelength, here's 1 wavelength, here's 1.5. So starting down low, you can see that the impedance of the antenna is only about 10 ohms. And we go up to 40 ohms as we go up higher. And then there's 50 ohms. And then it goes up higher. And then it goes up even higher. And it goes up to close to 100 ohms. And then it starts coming back down again as we continue to go higher. And if we look at this and we take the average of these peaks and valleys, the nominal impedance, depending on the height, that's where we get the 73 ohms from. But in your case, if you're down here under a half of a wavelength, the height of the antenna may have a huge bearing on what the impedance of the antenna is. So always keep that in mind, because people will say, well, should I trim ends of the antenna, or should I add extra wire? That's one way to change the resonant point, but I might have you first just try raising or lowering the antenna if you can, and see if you can get a better impedance match. Now, what I showed you before that chart was for perfect ground. Here's perfect ground. That doesn't exist, of course, so in the real world, this is the kind of thing that happens, that you start about here and work your way up. The same phenomena occurs. We looked at the isotropic radiator earlier, and I told you that manufacturers measure their gain of an antenna, a commercial antenna, against either the isotropic or a dipole that is cut for that frequency. And a dipole has 2.15 dB more gain than the theoretical isotropic radiator. So just keep that in mind. If a whiz-bang antenna is rated at 8.15 dBi, in comparison to a dipole, it's only 6 dB stronger. But 6 dB is pretty good. That's 1 S unit, so that would be a good antenna. All right, questions? Well, I told you there's no questions in this section because I made this section up. But I just wanted to review that material for you so you had it complete. All right, dipoles and ground planes, section 7.1. So we saw the half-wave dipole, stretched out. We said its nominal impedance is 73 ohms. Well, a quarter wave vertical antenna is just a dipole antenna with one leg set 90 degrees. So here's here's a quarter wavelength vertical element up here, and here's another quarter wavelength going over here. That constitutes an antenna. Now, normally we'll put more radials than one down, and this is showing 4 radials. So the feed point, again, is at the center of the antenna, and the radials could be in the air, on the ground. And what is the impedance of a ground plane antenna? It's half that of a dipole antenna, so about nominally 36 ohms. And ground-mounted verticals, we want to put down as many radials as we can. The optimum number at a convention I heard a paper given is about 36. If you can get 36 radials down, that's doing good. But you put down what you can, as many as you can. And if they're on the ground, you put them on the surface. You don't have to bury them, or just an inch or so down if you need to bury them. My experience is if you lay ground radials on the ground and secure them with staples or spikes, the grass will grow up over them and you won't see them after about 2 weeks anyway. And so here we have a multi-band vertical antenna with quarter wave elements for, in this case, 20, 15, and 10 meters. This is exactly what Callum McCormick sells. The DX Commander. The DX Commander Classic antenna is built on this principle, where you have multiple driven elements for different frequency ranges and radials underneath it. Now, one adverse thing about vertical antennas is that they are coupled closely to the ground. And it depends on the soil conductivity where you are. It's very poor here in South Carolina. And so ground reflection losses, when the signal comes off the antenna, it goes down to the ground and bounces back up again and interferes with the pattern. Vertical antennas suffer from ground reflection losses, whereas horizontal dipole antennas don't. So they don't have the same problem. So just keep that in mind. I mentioned that the nominal impedance of a quarter wave vertical antenna is about 36 ohms. That's what we're looking at here, driven element and the radials. And that gives us, with 50 ohm coax, the lowest you can go is 1.39 to 1, which is a pretty good SWR measurement, but it's not 1 to 1. Now, if you can elevate the feed point of this antenna, and if you can take the radials and slope them downward, then you can use this principle to get the feed point impedance to be 50 ohms and get 1-to-1 SWR match. Will you get any more power output than the other antenna? Would it be noticeable? Probably not. But I just want you to know that this principle of using bent radials to match to 50 ohm feed line is a very popular one, especially at VHF and UHF, where the antennas are much smaller. Speaking of smaller antennas, loaded antennas. No, I'm not talking about firearms. Remember the formula, 468 divided by the frequency in megahertz will give you the antenna length in feet. So for a 3.5 megahertz antenna on the 80 meter band, you're at 130 feet. That's pretty big, all right? And an antenna, a resonant antenna, is a resonant circuit. So here we have a simplified view of a series resonant circuit where, and at the frequency of design, in this case 3.5 megahertz, the capacitive reactance of the antenna is going to be equal to the inductive reactance of the antenna. They will cancel out, and all you're left with is radiation resistance. This is the thing that takes the power from your transmitter and radiates the energy out into space. That's the antenna's job. So that's what we want. Have you looked at the formula for calculating the resonant frequency of a circuit? Here it is. We don't go into it in depth here in the general class. We'll look at it more in the extra class. But what I want you to take a look at is the relationship between frequency and inductance and capacitance. It's an inverse relationship, 1 over. So increasing inductance here will give you a lower resonant frequency, F. Or increasing the capacitance will give you a lower frequency, F. And this is the concept of loading an antenna, and it comes into play with mobile antennas for sure. So we're using a vertical antenna. In the case of a mobile, the ground plane is actually the chassis of the vehicle itself. And you can add inductance. Here we have an inductor added at the center. Or you can add something called a capacitive top hat at the top of the antenna. Both of these are techniques to load the antenna, to make the antenna look electrically longer than it is, which is why you can have a whip antenna on a car that's less than 10 feet tall and still be able to operate on 80 meters because of loading, because of the addition of an inductance or capacitance or both. Now, you don't get something for nothing. The trade-off is a reduced operating bandwidth. So if we look at a VSWR plot for a full-size antenna on the left, you can see that's pretty broad. It's covering, in this case, pretty much all of the 20-meter band under a 2-to-1 SWR. That's pretty good. With a loaded antenna, however, also known as a high Q antenna, the operating bandwidth is very small. So only right about here is are you going to have optimum performance, which is why hams came up with motorized inductors. And when they first built these sorts of antennas, they actually took the motors out of these electric screwdrivers, these rechargeable screwdrivers. They're 12 volts, so you could use them in a vehicle, and they mounted them here in an assembly, and they could rotate this, and this is an inductor here that could go up and down and change inductance from controls inside the vehicle. So you could actually then use this to go on multiple bands from the same antenna, or sometimes even changing the whip length also would impact what band you're going to work on. So if you hear somebody talk about a screwdriver antenna, this is what they're talking about. Not to be confused with, you'll find these on HT whips and also on mobile. This is what is known as a corona ball. It is not capacitive loading. What it is its purpose is to reduce high voltage discharge from the tip of the antenna on transmit. Remember, the high current point is going to be at the base, and the high voltage point of this antenna is going to be out here. And you can actually draw arcs from this sometimes in the right humidity conditions. So that's what this corona ball is all about, is to reduce those arcs and sparks. We'll talk more about this particular antenna, but there is a question in this section, so I'll just mention it now. Near vertical incidence skywave antennas. These are typically half-wave dipole antennas that are purposely mounted low to the ground, like 1/10 of a wavelength, and may even have a reflector mounted underneath it. Why would you want to do this? Well, this is an antenna that will send energy directly up to the ionosphere and have it bounce and come right back down in a local coverage area. This is great for tactical communications in mountainous areas, for example, where VHF or UHF can't go through the mountain, but you could send an HF signal up to the ionosphere, have it come right back down on the other side of the mountain, and establish communications. Well, we'll talk about NIVIS here again, but I just wanted you to see that now. All right, let's answer some questions together and see what we retained. So what is the purpose of a capacitance hat on a mobile antenna?
Charlie?
Everybody see that? It's to electrically lengthen a physically short antenna. And what is the purpose of a corona ball on an HF mobile antenna?
Delta?
It is delta, to reduce the RF voltage discharge from the tip of the antenna while transmitting.
And protect your eyeball.
That too. So what is one disadvantage of using a shortened mobile antenna as opposed to a full-size antenna? Charlie is right. The operating bandwidth you saw may be very limited. And which of the following is a common way to adjust the feed point impedance of an elevated quarter wave ground plane vertical antenna to be approximately 50 ohms?
Bravo.
Bravo, yes. Slope the radials downward. Very good. And which of the following best describes the radiation pattern of a quarter wave ground plane vertical antenna?
Delta.
It is. It's omnidirectional in azimuth. And what is the radiation pattern of a dipole antenna in free space in a plane containing the conductor?
Bravo.
Yeah, I don't like this question. The answer makes sense, but the question doesn't make sense to me. The answer is alpha. It's a figure 8 pattern at right angles to the antenna. That's the radiation pattern of a dipole antenna. Don't worry about that free space in the plane containing the conductor. I don't like that part of the question, but remember that it's right angles to the antenna for a dipole. All right, how does antenna height affect the azimuthal radiation pattern of a horizontal dipole HF antenna at elevation angles higher than about 45 degrees? What a question.
Charlie.
It is, Charlie. If the antenna is less than a half of a wavelength high, then the azimuthal pattern is almost omnidirectional. So where should the radial wires of a ground-mounted vertical antenna system be placed?
Charlie.
Yeah, on the surface of the ground or buried a few inches below the ground. And how does the feed point impedance of a horizontal half-wave dipole antenna change as the antenna height is reduced to 1/10 wavelength above ground?
Bravo.
Yeah, it was that first part of that chart where I showed you was the most important thing. It decreases as you go lower to the ground, certainly over perfect ground. And how does the feed point impedance of a half-wave dipole change as the feed point is moved from the center toward the ends?
Alpha.
Right. It steadily increases, 200 ohms there at that 1/3, 2/3 point, and very high at the ends. So which of the following is an advantage of using a horizontally polarized compared to a vertically polarized HF antenna?
Alpha.
Yes, horizontal antennas don't suffer from ground losses, ground reflected losses, as do vertical antennas. And what is, okay, here we're doing some calculations. What is the approximate length for a half-wave dipole antenna cut for 14.25 megahertz? So they want the answer in feet, so remember 468 divided by.
That's a 20 meter.
Alpha.
Alpha. Yeah.
Not alpha, but it is, I heard somebody, delta. 33 feet for a half-wave dipole antenna. All right, you'll have another chance here. Come on. What is the approximate length for a half-wave dipole antenna cut for 3.55 megahertz?
Charlie.
Yeah, so 3.55 is 80 meters. I mentioned it earlier. It's about 130, 132 feet. Yep. All right. Listen carefully to this. What is the approximate length for a quarter wave monopole antenna cut for 28.5 megahertz? You can use the same formula
Alpha.
and then divide by 2 to get to quarter wave. Yes, 8 feet. And how does antenna gain in dBi compared to gain stated in dBd?
Alpha.
No.
It's higher. It's
Bravo.
higher.
Yeah.
Bravo.
Bravo. Gain in dBi is 2.15 higher than that of a dipole, which is why manufacturers like it, because it makes their antennas look like they have more gain. So read the fine print. All right. Which of the following antenna types will be most effective as a near vertical incident skywave antenna for short skip communications on 40 meters during the day?
Alpha.
Yeah, it's very low to the ground, so a horizontal dipole placed between 1/10 and 1/4 wavelength above the ground is a NIVUS.
Is it the same thing as a beverage antenna?
No, we'll talk about beverage coming up.
Beverage is receiving.
Correct, yeah.
Oh, that's right. Yeah, that's right.
So what is the feed point impedance of an end-fed half-wave antenna?
Bravo.
No?
Delta.
Remember, end-fed, you're feeding at the end of the antenna. That's a very high voltage, low current point. So it's a very high impedance. The ratio of voltage to current is very high. And how does a screwdriver mobile antenna adjust its feed point impedance?
Charlie.
Very low.
So it doesn't extend and retract the whip. I'm sorry if I confused you on that one. The motor is actually turning that inductor. So it's Bravo, yes, by varying the base loading inductance. It's shorting out part of the inductor so it's not even in the circuit, so yeah. So what is the common name of a dipole with a single central support?
Alpha.
Yep, that's an inverted V, very popular antenna. All right, moving on. Yagi antennas, section 7.2. So the driven element of most Yagi or beam antennas is a half-wave dipole antenna. And one characteristic that you can actually play with yourself with half-wave dipoles and Yagis is the diameter of the elements. A greater diameter element will give you greater SWR bandwidth. And he's since taken them down, but there was a ham in Piedmont, not too far from here, who had cage dipole antennas like this. I wish I had taken a picture of them. I forgot to do that. They looked awesome, and I can imagine that the SWR bandwidth was very broad on these antennas. Well, the same kind of thing happens with Yagis, and it's the reason why some Yagis are inexpensive and some are much more expensive. It can have as much to do with how large the diameter of the elements are. So this little high gain TH3 Junior over here has got narrow elements. The aluminum's not very big, whereas on a Mosley, well, they're big. They're rugged, and higher bandwidth is a result in many cases. And remember, we talked about bandwidth, low Q, wide bandwidth, high Q, narrow bandwidth. So that's something to consider. All right, we looked at a vertical antenna earlier, and a famous axiom about vertical antennas is that they receive and transmit equally poorly in all directions. Some people don't like vertical antennas, but they have their role. And one interesting phenomenon about a vertical antenna, which makes the DX Commander antenna that I talked about before so interesting, is its low angle of radiation. The primary radiation from the antenna comes down very low to the horizon, and because of that, it's good for DX because the signal goes way out to the farthest point on the ionosphere before it is refracted back down. So that's great with a vertical antenna. And with a vertical antenna, you don't have to worry about pointing it in any direction, which is a disadvantage with a Yagi. You got to know which way to go. Which way am I going? One thing that can help is something called an azimuthal projection map. This is a map of the world that is centered on your location, on your QTH, and it shows you the bearing to go for various countries in the world, so that if you do have a directional antenna, a Yagi beam or whatnot, you know which way to point it. And there is this website, I checked it, it's still active, NS6T. He's creating custom azimuthal maps for free. So if you go to this URL and request a map with, give him your coordinates, your latitude and longitude, or maybe Maidenhead coordinator, I can't remember, and he will send you back a PDF with your own azimuthal map centered on your location. ARRL also sells these maps, general maps that are centered on the center of the United States, which are approximate. You know, that's a good start anyway. With a Yagi antenna, sometimes more important than what you can hear is what you don't hear. So if you have a directional antenna that has a very strong null, like this antenna, which is in a cardioid pattern or heart-shaped, it's upside down heart, but okay, you can point the antenna away from the noise source. If you've got an interfering noise going on, null that out and maybe hear the signal of the station that you want. So that's another beautiful thing with directional antennas. Now, Yagi antennas, the basic Yagi antenna uses a half-wave dipole as the driven element, probably center-fed, but then it adds some additional elements. A director element, which is about 5% shorter than the driven element, and a reflector element that is about 5% longer. And these are what we call parasitic elements. They're not, the coax connects to the driven element here. These are not connected to the coax, but they're in proximity, and they help shape the pattern of the antenna parasitically. And you can have, this is a 3-element Yagi, but you can have 5-element Yagis as well. You can change the boom length. This is called the boom down here. You can add more directors, or you can adjust the spacing. All of this, you get increased gain and a narrower beam width. That means that the beam is going to be tighter because of the additional elements. And one characteristic of a beam or Yagi antenna is its front to back ratio. It's the ratio of signal strength in the main lobe out here, as opposed to that signal strength in the reverse direction here. So this is the main lobe, this is the back lobe, and here's some minor lobes off to the side as well. So I mentioned you could make those changes, and you can do it experimentally. You can build antennas, but we've moved to computers. And computer modeling of antennas is a really big thing. Probably the most powerful available to the amateur radio community is EasyNEC. And it used to be EasyNEC was a commercial software, but W7EL retired, and he said, I'm going to give it to the ham radio community for free. So the URL is down there at the bottom, easynec.com, and you can download his last version, version 7, and install it on your computer for free. That's one alternative. There's a steep learning curve, but it's a very powerful piece of software. Another free bit of antenna modeling software is something called Monogal, which was developed by Japanese and German amateur radio operators. And you can also download that for free. The URL is there. I mentioned Cal McCormick and DX Commander. Well, here is the DX Commander, and just this week he's come out with, I've only got the first 2 series here, antenna modeling for beginners using Monogal. And so you might want to take a look. He starts out with dipoles, does an inverted V next. He'll do verticals in another section. Really, you can follow along, download the software, follow what he's doing, and you can learn how to model antennas. When you're doing this, the things you want to consider is, the physical length of the boom for a Yagi, or the number of elements on the boom, or the spacing of each element along the boom as well. Here we have that coax, for example, and going to the driven element. Now, when we add these parasitic elements, you don't get something for nothing. Here's our 3-element Yagi. But when the parasitic elements are added, it actually reduces the impedance here at the center of the dipole from nominally 73 ohms down to maybe 20 ohms, because these are taking power from the main antenna. And so we have to impedance match to get back to 50 ohms. And one of the most popular ways to do that is something called a gamma match, which is an arrangement with a capacitor, maybe variable, and an inductive rod out here to drive one element of the dipole. Here's another look at a gamma match antenna. This is a way that you can match that lower impedance, because of the parasitic elements, back up to 50 ohms. Another thing that manufacturers can do, or you can do in your design, is make the center element, the half-wave dipole, shorter than it really is at resonance. And then you can add an inductor at the center. In this case, the inductor is this U-shaped piece of wire. Note that the antenna is not directly connected to the boom anymore. It actually is insulated in these plastic insulators. So you've got a quarter wavelength over here, quarter wavelength over there, but a little shorter than a quarter wavelength. And this additional inductance cancels out the capacitance of the short antenna and brings the impedance back up to 50 ohms. This is also called stub tuning, where you're actually connecting this U shape here. It can be done with ladder line. You can use that as the stub. You say, Gary, that you're putting a short circuit right across that. It's a short circuit at DC, yes, but at RF, it is not. At RF, it acts like an inductance. And you'll also find Yagi antennas are designed for multiple bands. If you're putting up an antenna, you'd like to be able to use it on more than one band maybe, so you can install traps, these little devices here, or you might buy a Yagi antenna that uses traps. And what happens, these are filters that allow the center part of the antenna to be used for the highest frequency range. The next band you'll use more, and the next lower band you'll use all of the antenna. So here's a tri-band or a 3-band trapped Yagi antenna, maybe for 20, 15, and 10 meters. Traps allow for multi-band operation. Okay, we're over to questions. So which of the following describes an azimuthal projection map?
Bravo.
Yeah, it's a map that shows true bearings and distances from a specific location. And which of the following would increase the bandwidth of a Yagi antenna?
Alpha.
Yep, make the elements larger in diameter. And what is the approximate length of the driven element of a Yagi antenna? Yeah, it's our famous half-wave dipole. And how do the lengths of a 3-element Yagi reflector and director compare to that of the driven element?
Alpha.
Alpha is correct. The reflector is longer and the director is shorter. And what is the primary effect of increasing boom length and adding directors to a Yagi antenna?
Alpha.
Yep, the gain of the antenna will go up. And what does front to back ratio mean?
Charlie.
Yeah, it's the power radiated in the major lobe compared to that in the opposite direction. And what is meant by the main lobe of a directive antenna?
Delta.
Delta.
It is delta. It's the direction of the maximum radiated field strength from the antenna in that direction. And which of the following can be adjusted to optimize forward gain, front to back ratio, or SWR bandwidth of a Yagi antenna? Read carefully.
Delta.
Delta.
It is delta. The physical length of the boom is one, the number of elements on the boom is another, and the spacing of the elements is another. All of those choices are correct. And what is a beta or hairpin match?
Alpha.
It is alpha. It's a shorted transmission line stub, or that U shape you saw there, placed at the feed point of a Yagi antenna to provide impedance matching. And which of the following is a characteristic of using a gamma match with a Yagi antenna? I don't know if you observed this.
Alpha.
It is alpha. It does not require the driven element to be insulated from the boom. That was a difference between the hairpin match, where you had to be insulated from the boom, and a gamma match. The center of the driven element can be directly connected to the boom. Ladies and gentlemen, you've been doing great. It's time for you to get up and move around, stretch, go get something to drink. Let's take 5 minutes, and we'll be back whenever we can. So come on back.
Push.
Welcome back. So glad to have you with us, and hope you got a chance to stretch a little bit and move around, and we'll get going here. We had a little discussion in the break there in the Zoom classroom, and somebody mentioned loop antennas. Guess what? That's next. Section 7.3, loop antennas. And I want to point out that amateur radio or ham radio is an experimental hobby. You want to experiment. You want to try things out for yourself. So come back to the laptop for a second there, Dave. Whoops, there we are. There we go. Ham radio, the experimental hobby. And one of my favorite quotations is this one, and I didn't really know who to attribute it to, but the internet says that our great New York Yankee catcher, philosopher, Yogi Berra is responsible for this one. In theory, there is no difference between practice and theory. In practice, there is. What do I mean by that? Well, we look at some loop antennas, and I had to figure out what this contradiction was. If a loop antenna is small, less than 1 wavelength long, so here's a loop antenna that could be transmit and receive, or could be just receive, not very big, sitting out on somebody's deck. The directionality of this loop is in the plane of the loop. So it's directional left and right as we're looking at it right here. Whereas if you have larger loop antennas, greater than 1 wavelength, then the directionality, theory says, is to be 90 degrees from the plane of the antenna. So in this case, away from us and toward us. That's the direction perpendicular to the plane of the loop. And as was mentioned in the break, that with vertical loop antennas, which are these here, they're oriented vertically. These are large antennas, greater than 1 wavelength. If you feed it here at the side, then this becomes a vertically oriented antenna. If you feed it down here, it becomes a horizontally polarized antenna. Vertically polarized, horizontally polarized. They're both vertically oriented, but this is vertically polarized and horizontally polarized. These are HF antennas that we're looking at here, considering. And then horizontally oriented here, if you feed, either I feed mine at the corner, but they're talking about here in the center. This is a horizontally oriented and horizontally polarized antenna. And okay, I grudgingly have moved to looking at AI. Google AI says that horizontal loops parallel to the ground are generally quieter, yes, offer higher gain for regional coverage, and act as cloud burners, sending radiation up to the ionosphere, whereas vertical loops perpendicular to ground provide better low-angle radiation. Come back to me just for a second, if you would, Dave. You saw maybe on an earlier slide, I mentioned the Greer Amateur Radio Club. I'm a member of that club, and we had a presentation at our last meeting by another ham who was doing a presentation on vertical loops and how disappointed he was in the performance of his vertical loop. And he put the loop up based on an earlier presentation that I had done on horizontal loops. But he also then talked about the theory and talked about how horizontal loops are cloud warmers. And I thought, that's not my experience. The theory says that, but that's not what I have experienced. So come back to the presentation. The question was, is this a cloud warmer? And this is the kind of loop antenna that I have up. I've got 2 of them, actually. I've got an 80-meter full wave loop, and I've got a 160-meter full wave loop. These are multi-band antennas, so they'll work on all bands as well. I feed mine at the corner of the antenna, and I feed it through a 4-to-1 hybrid balun from Balun Designs. And it's about 40 feet up. Both of them are 40 to 50 feet up. An 80-meter loop like I have is about 272 feet in length total. 160 meters is twice that. And it is a resonant antenna on the lowest band, but it'll also work on multiple bands. And so recently there was a DXpedition on the air from Bouvet Island. 3 Yankee 0 Kilo was the call sign. And this is the performance of my 80-meter horizontal loop, calling them on 80 meters using FT8 in the first 2 minutes. And I did a quick screen capture. I'm up here. Bouvet is down here in the South Atlantic. This is Antarctica. This is the German station down in Antarctica. And my horizontal loop antenna, the Cloud Warmer, was going over to Europe, no problem. Going down to Central America, no problem. Going down to Antarctica, no problem. Now, I never made the 80-meter contact with the Bouvet DXpedition. But I tried, and my signal was reaching down in that area. So this is what I was using, this exact same antenna on 80 meters. Later, I used this antenna on 15 meters, calling Bouvet. Note here on 15 meters, I had great signal strength here in the United States, great signal strength here in Europe, down to Antarctica, and again, Bouvet down there. I never did get them on 15 meters either, but this was the pattern. The thing was that I did get them on 40 meters using this antenna. I did get them on 20 meters, 12 meters, and 10 meters. So I got them on 4 bands. But I say, based on my experience, a horizontal loop is not a cloud warmer. And I think a lot of it has to do with the polarization of the antennas. Now, we say that when you're sending a signal from a transmitting station up to the ionosphere, that let's say you're using a vertical antenna, it doesn't matter whether the receiving antenna over here is horizontal or vertical, because the ionosphere will tumble the polarization of that. Dave's going to probably talk more about this next week. We say that instead of a linearly polarized, this is in case vertical or polarization, that you get an iopic polarization where you have both vertical and horizontal polarization elements coming down from the ionosphere. In my experience, have been surprised that sometimes there's very much vertical and very little horizontal, or sometimes very much horizontal but very little vertical. It all depends on the makeup of the ionosphere at that time. To back me up that horizontal loops are not cloud burners, I got a chance to meet Don Keith a couple years ago, N4KC, at the Huntsville Hamfest. This is an antenna that he has up in his QTH. It's a non-resonant antenna, so it's not designed for any particular band. It's 475 feet long, omnidirectional with many lobes in various directions, and he contends low angle of radiation. Now, he doesn't use a 4-to-1 balun like I do. He feeds it with 450 ohm ladder line and then uses an antenna tuner with a balanced output. He gets great results with this antenna. So this was one of the things that motivated me to try to put up horizontal loop antennas. Another advantage of loop antennas, as opposed to Yagis, is that, remember, with a dipole antenna, you have a high voltage at the end of a Yagi or a dipole antenna. This was a problem for Clarence Moore, a Christian missionary and broadcast engineer at the religious broadcaster HCJB in Quito, Ecuador. He was using Yagi rotatable antennas for the broadcast station, and in the high air of the Andes Mountains, the tips of his Yagi antennas were arcing off, and he was always having to go up and replace them. So literally, there's a book about it. He prayed about it and came up with this design, which is known as the cubical quad antenna, which is 2 loops, a driven loop, and then another loop that could be either a reflector or a director. And the cubical quad's properties is that the driven element is a full wavelength long, a reflector element would be 5% longer, or a director element would be 5% shorter. It's mechanically a little difficult to support the loops and get them out there, but a 2-element cubical quad has the same gain as a 3-element Yagi. Also, you can feed it directly with a 50 ohm coax. You don't need to do any gamma matching or hairpin matching. They work very well at low heights, 35 feet. I have a friend who's a ham up in Michigan that uses cubical quads at not very high up, and they work great. And they have a broader SWR bandwidth than a Yagi antenna. So there's a lot to merit cubical quads. Feed point where you feed them, they can be either horizontal or vertically polarized, depending on where you feed them. And they can be multi-band. You can build multiple cubic quads on the same mechanical support. This is called a spider beam quad, I think it was. And you feed them with one coax. It's kind of like the hex beam that you see, which is a 2-element Yagi type antenna, also fed with one coax. So very interesting. And cubical quads in this case can be squares, or you can have delta loop quads as well. And if you were going to put up a 2-element delta loop, again, it has the same gain as a 3-element Yagi. The driven element is a full wavelength, so each leg is a third of a wavelength. And again, if you're going to have a reflector, it's 5% longer than the driven element. A director would be 5% shorter. So on VHF and UHF, you can build directional antennas, but sometimes it's hard to know where the signal's coming from. They're so directional. They might be 10 elements, 20 elements long, and that makes a very narrow beam width. So they came up with this antenna called a halo antenna. This halo antenna is horizontally polarized, and the plane of the antenna, it's omnidirectional in the plane of the antenna. So you can have this antenna up, be listening for weak signals, maybe hear their call sign or hear their Maidenhead locator and say, okay, that's where I got to point the directional antenna, and boom, you'll make the contact. So this is a halo antenna. Not to be confused with receive loops. You can find receive-only antennas like this. This is the Wellbrook. I've got one of these downstairs. They're rotatable. They're smaller than one wavelength. Again, the directionality is in the plane of the antenna. They also make these for transmit as well, sometimes called magnetic loop antennas. It depends on how you're coupling to them. Sometimes you're directly coupling, sometimes you're inductively coupling, and you have a tuning element here to tune the antenna to particular frequencies. If you really have a space limitation, but you really want to get DX and whatnot, one of these could work for you, possibly. It's an Italian design. It's an automatic magnetic loop. It learns your transmitter and your location and the settings to achieve resonance at the various frequencies. It's about $2,000 plus tariff now. So it's probably not what you're going to want to get. But again, in this case, because it's smaller than one wavelength, it's directional in the plane of the antenna. All right, questions? So in which direction is the maximum radiation from a VHF-UHF halo antenna?
Charlie.
It is omnidirectional in the plane of the antenna, or of the halo. And in which direction or directions does an electrically small loop, less than 1/10 of a wavelength in circumference, have nulls in its radiation pattern? Nulls.
Charlie. Oh, no.
Look at that again. You're close. So if it's maximum in the plane of the antenna, it's going to have nulls broadside to the antenna. So small loops, directional in the plane of the antenna, nulls are going to be broadside to the antenna. All right. Specialized antennas, you can just throw a wire up into a tree and connect your transmitter to it. Is that advisable? No. because that's what we call a random length end-fed wire. As shortwave listeners, we always used to use those for our radio receivers, but for transmitting, it's not so good because you're bringing an end-fed antenna, the high voltage RF point, into your ham shack. That's not good. You may get a shock or an RF burn, so that's probably something you don't want to do, because remember that end of that antenna, even if it's a random length, that's going to be a high voltage point. You don't want to do that. All right, another kind of specialized antenna, we talked about Yagi antennas. What about two Yagi antennas? Yeah, you can do it. You can stack two identical antennas, and it will result in a 3 dB additional gain in the forward direction versus a single antenna of like-minded. And so these are vertically polarized antennas that are horizontally stacked. Or you can have vertically stacked antennas. In this case, these are horizontally polarized antennas with one above another. And what happens in this case, the beam width minimizes in the vertical plane, whereas in the previous version, the beam width minimized in the horizontal plane. Vertically stacked antennas reduces the vertical beam width, or the elevation. And my friend Bob, ND7J, did this with a couple of 3-element 6-meter Yagis at his QTH. This was the tower, and we helped him get them up in the air. And he has such good luck with these that I actually did the same thing here at my QTH. I didn't have a lot of room, so I stacked 2-element over 2-element, but it did reduce beam width and give me additional gain, so I was very happy with that. Now, if you want to do Earth, Moon, Earth on 6 meters, you're going to probably need to do something like this, which is called an H-frame. You can guess why. And with 4 antennas, you'll get 6 dB of gain. And you get both reduced vertical and horizontal azimuth beam widths. So this is the culmination of stacking Yagis. NIMBUS, we talked about before, the near vertical incidence skywave. Low antennas close to the ground, maybe even with a director. Shoots energy up purposely to the ionosphere, where it'll come back down in your local area. And we talked about traps. We talked about traps for Yagi antennas. You can add traps for horizontal dipole antennas as well. It enables multi-band operation with just one antenna. The thing to keep in mind with this type of an antenna, though, is that it isn't a single band antenna. And sometimes a single band antenna is good because it only transmits signals in that frequency range, and it rejects transmitting harmonic signals, things like that, whereas multi-band antennas will transmit harmonic signals. So if you're using an older transmitter that maybe it doesn't have a very clean output, that could be an issue. Log periodic antennas are another kind of directional antenna. They don't use traps. But they are a wide bandwidth antenna. There's continuous operation over a wide range of frequencies, and the spacing between the elements and the length of the elements varies continuously logarithmically. It does not suppress harmonics, much like the other multi-band antennas. This one is pretty big, but you'll see a bunch of these over the various embassies in Washington, D.C., because all of the countries there at their embassies use these for diplomatic communications. On the ground, this is a little easier to see the logarithmic relationship. You can see the wider spacing here from here than it is here, and how it varies as you go up in frequency. So this is a wide band antenna. In this case, this is a military style that they would use for a fixed application in order to, and it's a series of inverted V's, as you can see, which is providing gain in this direction over here. Somebody asked about a beverage antenna during the break. It's designed by Harold Beveridge, originally for AT&T. They were trying to, at that time, to get international telephone communications. It was done by radio, and they wanted to get more reliable communications with England, for example. And so they came up with a Beveridge antenna, which is a very, very long wire, multi-wavelength if you can do it, that terminates into a 450 ohm resistor. And this horizontal wire points toward where you want to receive from. It's a receive-only antenna because it has negative gain. It doesn't add anything to the signal, but one big benefit of it is noise immunity. So this is kind of what it looks like. You feed it with coaxial cable. This is what hams do anyway. 4-to-1 balun or 1-to-9 balun, depending on what you're using. Grounding over here. Here's our long beverage antenna. 20 meters long here, well, longer than that. The original beverage antenna was miles long, by the way. And then a load, a non-inductive resistive load here, 450 ohms. And when signals come in from the resistor side, think signals coming from England, they build up a voltage along the length of the antenna. This is what is known as a wave antenna or a traveling wave antenna. And then it is sent on to the receiver, and you can use this to receive very weak signals. Hams use beverage antennas for the low bands, 160 meters, 80 meters, and even 40 meters because they have really good reception characteristics, better than the transmit antennas would. And they are immune to noise, they're much quieter. Beverage antennas are typically between 4 and 10 feet above the ground. Although you can put beverages lying on the ground. They're called bogs, beverage on ground. And people sometimes have very good luck with them. Again, this is an experimental hobby. All right, more questions. So what is a characteristic of a random wire HF antenna connected directly to a transmitter?
Bravo.
Not Charlie.
Bravo.
Bravo, yes. Station equipment may carry significant RF current. You may get zapped, you may get RF burns. You don't want to do that. In free space, how does the gain of two 3-element horizontally polarized Yagi antennas spaced vertically a half wavelength apart typically compare to the gain of a single 3-element Yagi?
Bravo.
Yep, 2 antennas, twice the signal, 3 dB higher. And what is the primary function of antenna traps? To catch antennas, of course.
Alpha.
Yes, to enable multi-band operation. And what is an advantage of vertically stacking horizontally polarized Yagi antennas? We went over it kind of quick. But if you take 2 horizontally polarized antennas, put them on top of each other, they narrow the main lobe in elevation. Gives you additional gain in that direction. And it actually reduces the angle of radiation, so you get more DX. So which of the following is an advantage of a log periodic antenna? It is alpha. Log periodics are very wide band. They'll actually cover frequencies in between the ham bands. That's why the diplomatic services use them, because they can energize any frequency they want, and the antenna will work. All right, which of the following describes a log periodic antenna?
Alpha.
Yeah, element length and spacing vary logarithmically along the boom, as opposed to linearly. All right, what is the primary use of a beverage antenna?
Alpha.
Yep, it's directional receiving for medium frequency and low HF bands. And which of the following is a disadvantage of multi-band antennas?
Delta.
Delta. They have poor harmonic rejection. They can actually transmit on, if you've got a multi-band antenna, it can transmit on the next band up, or 3 bands up, or whatever. All right, very good. Section 7.5, feed lines. And what we're looking for maximum transfer of power is a matched condition. We want the output impedance of our transmitter, here's our generator, to be, let's say, 50 ohms. we feed coaxial cable of 50 ohms, and we feed our antenna, or the load, of 50 ohms. When they all match, you get the maximum transfer of power. Power coming from the left-hand side, which is depicted here as this pulse, is absorbed by the radiation resistance of the antenna and is radiated. And all of the power is radiated out. This is what we want, but it's not typically what we have or what we get. I did want to point out, when waves from the ocean come toward, for example, a cliff face like this, you'll actually see the waves bounce back, bounce off of that cliff face. That's a rebound wave. And the same thing happens on a transmission line with a non-matched impedance. So here's an open circuit. We actually have forgotten to connect up the antenna, and we're sending power down the transmission line, and it's all being rejected and sent back down the transmission line toward the transmitter. This is 100% reflected power. That's not typically what we have unless we forget to connect up the antenna. What we typically have is a partial reflection of power, where some of the power is going to be absorbed by the radiation resistance of the antenna, but some of it comes back toward the transmitter. Note in this case the polarity changed, and that polarity change indicates that it's going to a load that is lower than the 50 ohm of the transmission line. So high impedance to low impedance gives you that inversion, whereas low impedance to high impedance, power comes back, but it stays the same polarity. That's more than you need to know, but these are great illustrations, I think, of the concept of forward and reflected power. And the most severe cases is open circuit, which is shown on the top, or a short circuit, where if you were to short the ends of the coax together, that's the bottom, where all of the power comes back, but it's reversed in polarity. So,
Won't that blow up your antenna or your transmitter?
yeah, the transmitter is not going to like that very much. The transmitters don't like high standing waves. So here's a case of standing waves. The blue line, if you can see it there, going from the left to the right, that's your transmitted power going from the transmitter to the load, to the antenna. And the red is the reflected power that is coming back from the antenna toward the transmitter. And you see where they arithmetically add together? That's the black line. That black line that's going up and down, but it's not moving. That wave, that black wave, that's a standing wave. It's standing on the transmission line. And it's because of the interaction between the forward and the reflected power. And yeah, that's not good. What we want is no reflected power, because if we have no reflected power, then you'll have a standing wave ratio of 1 to 1. Which is perfect. That's exactly what we want. That means that all of the power that we're sending is being radiated by the antenna out into space. And this concept has been around for a long time. People have known about it. In fact, here's our AT&T again in their archives. They put together a mechanical version of standing wave, where you can actually see as he makes the changes here. So the URL for the YouTube video is down there at the bottom. If you've got some extra time, I would suggest you take a look at this, look at reflections that AT&T put together. So how do we work around this? Well, if we have a mismatch condition, they're generally not super severe, we can deal with it using something called an antenna tuner, also known as an antenna coupler. And this box, which you're seeing here, this is an external one, has got a couple of variable capacitors, or probably capacitors over here, and a switched inductor. What this does is an LC circuit, or a complex circuit, that generates a rebound wave. So we're sending power from the transmitter, we're sending it out to the antenna, and a reflected power is coming back, and the antenna tuner says, no you don't, you go right back out to the antenna. This is all happening at the speed of light. So it's not anything that anyone would notice. It doesn't affect the audio quality or Morse code signals or anything like that. This is all happening continuously. The reflected power is rebounded and sent right back out to the antenna, where it may come back again, but it's sent right back out again, and the transmitter never sees it. The transmitter is setting its full 100 watts out, and it says, hey, I'm happy as a clam. It's all good. And so an antenna tuner sits between the transmitter or transceiver and the antenna. So here's the antenna tuner, and this is manually adjusted, but you can also have automatically adjustable antenna tuners. The antenna tuner can also be built into the radio, and most radios have them built in now as well. So here's a trick question. So what is the SWR on a transmission line between the tuner and the antenna after you're using the tuner? Let's say you get the transmitter happy, the transmitter thinks it's 1-to-1. But what is it on the transmission line going out to the antenna? The answer is it's still 5-to-1. You haven't changed anything. You just made the transmitter happy in using an antenna coupler or antenna tuner. And when we talk about SWR and impedance ratios, I just want you to know that, so if we had a 50 ohm transmitter going to a 200 ohm load, resistive load, that would be a 4-to-1 SWR. It changes a little bit when there's reactances involved, but we will ignore that for the moment. So 50 to 200, that's 4-to-1. 50 to 100 is 2-to-1. See the ratio? 2-to-1. 50 to 50 is 1-to-1. 50 to 25 is, again, 2-to-1. And 50 to 10 is 5-to-1. Note that for SWR, the big number is always the first one. But we're looking at the ratios between the feed point impedance, or the feed impedance, and the load impedance in this case. So we're probably not going to have a great match, but we want to get it as close as possible, because if we have high SWR and we have a transmission line that has line loss, and all coaxial cable will have line loss, then you lose power in the coax through heating. Now the coax won't catch fire, but this is to try to implant it in your brain. That high SWR causes higher total power loss in lossy cable. And so I put together this slide, but rather than go over it here, I'd like to go over to our demonstration area and show you something that I put together, and let's see if it maybe helps a little bit. So let me walk over to the demonstration area. So I call it bad juju. Lossy transmission line and high SWR. So over here we have our 100-watt transmitter. So the Flex Maestro will stand in for that. We've got our antenna tuner down here that is properly adjusted, all right? And we've got 100 watts, which I have cleverly put together 100 poker chips, representing our 100 watts, okay? And we've got a really bad feed line. It's got 3 dB of loss. That's half. So as our 100 watts goes out across the transmission line and goes to the antenna, by the time it reaches over here, it's not 100 watts anymore. We've lost half of it. We've lost 50 watts. That goes in the loss bucket. So now we've got 50 watts. And we've got a 6-to-1 SWR. And a 6-to-1 SWR is a 50% reflection. So 25 watts is going to be radiated by the antenna. That's good. That's what we want. But half, and the other 25 watts is going to be sent back to the antenna coupler, the antenna tuner. Again, 3 dB loss. So we're going to lose 12.5 watts. All right, that's going to be sent right back out again. Going to be sent down. Well, we're going to lose 3 dB again. Whoops. Losing 6 dB. There we go. So we're going to radiate 3, and 3 is going to be sent back down here again. This goes on forever. But we've kind of broken it down in just a one instantaneous instance. It's happening at the speed of light. You don't see this as any degradation of the signal. But the whole point is, we started out with 100 watts. In the end, 71.25 watts have been lost to the lost power bucket. We've only radiated 28.75 watts. So for 100 watts, we only radiated 28 because we had lossy transmission line and we had a bad SWR. Now, one thing about lossy transmission lines, and some manufacturers do this on purpose, especially for VHF and UHF. Have you ever wondered, you got a VHF antenna and they're using RG58 coax? Why are they using that? That has really high losses at VHF and UHF. We'll take a look. The laptop, please. With line loss and SWR readings, long lossy coax lines will make the SWR in the shack read lower or better than it really is. So if we take a look at our example from before, if we are sending out 100 watts, remember we lost 70 watts, but with the return power coming back, it adds up to only 14 watts, the return power. And because of that, that's the equivalent with 100 watts out, 14 watts back. That says the SWR is 2.2 to 1. When in reality, we know it's 6 to 1. So lossy coax can make the SWR look better than it really is. And here's a table which shows you that 2.2 to 1 is a 14% loss. So again, high SWR and line loss results in power loss in lossy cable. So that's not a good thing, bad juju. Now, ladder line has an interesting characteristic in that its loss per 100 feet is much less than coaxial cable. And so this is ladder line down here. It has a characteristic impedance of 450 ohms. A 300 ohm twin lead, the old TV cable, that looks like here, that has a impedance of 300 ohms. The impedance of these cables, it's based on the diameter of the conductors and the spacing between the conductors. So there's a formula if you want to go into it, but just be aware of that the characteristic impedance factors are the diameter and the spacing distance. And you can make your own. You do have to do some impedance transformation though, from 50 ohms up to 450. You've got to do that either at the antenna tuner or using a balun that's specifically designed for that. Most of us don't do that. Most of us use coaxial cable because it's so convenient. 50 ohm and 75 ohm are typical impedances for coaxial cable. Various types here, RG8X is very popular. No matter what type of coaxial cable you're going to use, though, the higher you go in frequency, the more loss you're going to have in that coaxial cable. And the loss is specified in dB per 100 feet. So here's a table of various types of coaxial cable and their loss per 100 feet. So here at 2 meters, for example, RG8X has a 4.2 dB loss per 100 feet, whereas LMR 400 has only 1.44 dB, which is why LMR 400 is recommended for use at the VHF and UHF. Okay, questions? So what is the purpose of an antenna tuner?
Charlie.
To increase the power transfer from the transmitter to the feed line. You're making the transmitter happy. If a transmitter, a solid-state transmitter, modern solid-state transmitter, sees a high SWR, it will reduce its power output. I think most radios will do this anything above 2 to 1 or 3 to 1 for sure. So your 100-watt radio all of a sudden automatically becomes a 50-watt radio or less. Which of the following factors determine the characteristic impedance of a parallel conductor feed line?
Alpha.
Yes, the distance between the centers of the conductors and they say the radius, but the diameter of the conductors. And what is the relationship between high standing wave and transmission line loss?
Bravo.
Yeah, we saw it there in the example. High SWR increases loss in a lossy transmission line. We only got 28 watts out of a 100-watt transmitter. And what is the nominal characteristic impedance of window line transmission line, also known as ladder line?
Delta.
It's the highest one there, 450 ohms, D. And what causes reflected power at an antenna's feed point?
Charlie?
Yes, it's the difference between the feed line impedance and the antenna feed point impedance. And how does the attenuation of coaxial cable change with increasing frequency?
Bravo.
Attenuation will always increase with increasing frequency. And in what units of RF feed line loss is it usually expressed?
Delta.
Decibels per 100 feet. And what must be done to prevent standing waves on a feed line connected to an antenna?
Delta.
It is delta. The antenna feed point impedance must be matched to the characteristic impedance of the feed line. You want the antenna to match the feed line. If the SWR on an antenna feed line is 5 to 1, and a matching network at the transmitter end of the feed line is adjusted to present a 1-to-1 SWR to the transmitter, what is the resulting SWR on the feed line?
Bravo.
Bravo.
Yeah, it doesn't change. It still stays 5 to 1. You've just made the transmitter happy. And what standing wave ratio results from connecting a 50 ohm feed line to a 200 ohm resistive load?
Alpha.
Remember, the big number is always first, so it's a ratio of 4 to 1, not 1 to 4. And what standing wave ratio results from connecting a 50 ohm feed line to a 10 ohm resistive load?
Delta.
The ratio between 50 and 10 is 5 to 1. And what is the effect of transmission line loss on SWR measured at the input to the line?
Alpha.
Yes, that was my example. That higher loss reduces SWR measured to the input at the input to the line, which is why I mentioned RG58 coaxial cable on VHF antennas. That's a lossy line. It makes the antennas look better than they really are as far as impedance matching. And that, ladies and gentlemen, is the end of Chapter 7. You made it. I am so proud of you. Let me go ahead and remove the spotlight for the folks in the Zoom classroom. Do we have any comments or questions?
I kind of want to know, whenever you're setting up an antenna to a transmitter, obviously you would want the most perfect match in the very beginning. So is everything based on just the feed line? Is that where, like, all this matching stuff, you know, is that what it is?
Yeah, generally, yeah. The transmitter itself is going to have a characteristic output impedance always 50 ohms. We typically use 50 ohm coaxial cable. So then the adjustment is going to happen at the antenna to get the antenna to as close to 50 ohms as you can. If you can get it anywhere under 2 to 1, you should be okay.
So it's really a matter of just buying the best coax, and that's that?
Well, buying good quality coax you don't have to buy LMR 400 all the time. RG8 works just fine for HF, but buying the appropriate coax for the frequencies involved, and then if the antenna can be adjusted to match that, then you get the maximum transfer of power.
On the loop antennas, when the wavelength is less, when the length is less than the wavelength, is it the total length of the wire?
Yes.
Of total circumference.
Yes.
And it literally flips orientation as soon as you get to the.
Yes.
There's no gray area. It just.
That's the rule I want you to know. Yeah.
Yeah. So
I've never tried that, but yeah, yeah.
So for doing DXing, if you you're in your backyard, you've got it horizontally oriented.
Right.
Okay.
And I say it's not a cloud warmer.
But if you wanted to use that antenna for higher frequencies, it would suddenly change its orientation to.
No, because it's always going to be longer. At higher frequencies, it's going to be multiple wavelengths long. It's one wavelength long at the lowest frequency of operation. So an 80-meter loop is one wavelength long at 80 meters, but at 40 meters, it's 2 wavelengths long. And at 20 meters, it's 3 wavelengths long. So, or multiples of that. So it's not going to flip orientation.
Okay.
But you will have different lobes coming away from the antenna. So if you take a look at the DX Commander, he does loop antennas as well, and you'll actually see that.
Does anybody use the beverage antenna for
Yeah, I've got 2 out in the backyard here that I use for reception. Oh, absolutely. They're inexpensive.
So you could have one antenna for receiving and another antenna.
Correct. And so that's where you want a radio that has a receive antenna input, which is interesting. The ICOM IC7300, the original little radio, did not. And that was always a criticism of the 7300. The new IC7300 Mark II has a receive antenna input. And the reason they did that is so you could use a beverage, for example, for the lower bands.
One last question about, so antenna tuners, they don't change this SWR. They just make the transceiver happy, right?
Correct. Yes.
Okay.
Absolutely.
Fooling the transceiver was the phrase used in the video.
Well, yes, and you're making the transceiver happy so that it will put out, for a solid state transmitter, it'll put out its full 100 watts. Yeah. All right, next week, propagation. That's the other half of the equation. The antennas get the energy up into the ionosphere, but then it's got to go someplace. So Dave, next week, what are you going to be talking about?
Right. Well, next week will be Chapter 8. We're going to cover the whole chapter. It's not a very long chapter, so we'll be able to get into some detail. And if time allows, we'll actually have a demonstration of how you can predict propagation from our location to one of the DXpeditions that are currently running out there. Of course, none of you probably have your general yet, so you won't be able to use that directly, but the principles will apply when you get to that point. So all of Chapter 8 for next week.
Very good. All right, thank you for your attention tonight. You've been great. Get up, move around, stretch, and we will see you next week for Chapter 8. Until then, 73, y'all.
73.
Everybody, thank you.
Sorry about my noisy dogs.
Hey, Gary. Gary,
Yes.
There he's gone.
Yeah, I'm here.
have you seen this guy on YouTube that goes around hooking up fence